All right, so now what we're going to do is we're going to pick up where we left off last time. So last time where we left off was that we were defining some of the ideas in unconstrained optimization. And so we had mentioned that there are the types of conditions that are important, like the first order necessary conditions, the second order necessary conditions for saying whether or not you have reached a minimum, and second order sufficient conditions, things like this. And then we started saying, okay, so based on that, certain things are going to be true about an optimum value, then how do we try to design algorithms to get us to the optimal value? And so we said that when you're designing algorithms to try to do unconstrained optimization of smooth functions, meaning that a sufficient number of derivatives exist of your objective function and constraints. But in this case, we have no constraints, so it would just be for the objective function. So algorithms for unconstrained optimization of smooth functions. And so, like we said last time at the very end, first you make a guess of the optimal values of the decision variables. And then the goal of an algorithm is that it should develop a series of guesses. And so the book by Nocedal and Wright refers to this as a sequence of iterates. From xk, from k equals 0 to however many you end up having. You could say, okay, an infinite number of iterates would be like this, but we really aren't going to want, not really want infinity of them in any reasonable algorithm. And the idea is that the algorithm should develop the sequence of iterates in a way that brings you toward the solution or the optimal values of the decision variables. And so the role of algorithm development for unconstrained optimization then in many ways is to say, what is this algorithm and what are algorithms that have good properties for developing the sequence of iterates? So the idea there would be, okay, so some of the things you might care about that the algorithm doesn't require too much storage, or that the algorithm only takes a few iterations to get you to a good enough answer, things like this. So that's going to be different for different problems, depending on what they look like from a mathematical point of view. And so algorithm development is about trying to make algorithms that work good in terms of things like memory and computation time for different problem classes. And so then you have to say, okay, how does it develop these iterates? Well, often the iterates depend on f and potentially its derivatives. At the current iterate and possibly prior ones. And so then we say, okay, that makes sense that algorithms are going to differ from each other. They're going to use information about the function at, for example, the current iterates. That would be something like if I evaluate the function that I'm trying to minimize at the current guess of the optimal value of the decision variables, it will tell me how large this objective function f is at that value. And if I look at like a prior one, for example, it would tell me, have I decreased f compared to previously? If I look at derivatives and things, it will tell me additional information. So we can see that this kind of information would be helpful for trying to analyze how do I need to change the iterates in order to continue to decrease f. And so with the goal is to decrease f to its smallest possible value and to find the value of the guess of the optimal value of the decision variables that does that for you. And so where we left off last time was that we were saying, okay, well, there's multiple ways that you could try to get the next iterate. And two common methods are for this unconstrained optimization of smooth functions is the line search and the trust region. And so where we left off last time is saying that what the role of the line search is that it is to choose the direction and search for a new iterate in this direction. From our discussion of directional derivatives, we have some sense of directionality in multidimensional space. And of course, you could generalize it beyond the figure that we drew in the lecture that included directional derivatives. But the idea being that as you go in a direction, your objective function is going to take different values. And so what you really want to do is something like this. You want to say, okay, I have a direction that I've already chosen, pk, but I want to know alpha, which is our step length, which we can see the idea by looking at this. So this says what we want to do is we want to minimize for alpha greater than 0, f of xk plus alpha pk. So this shows the idea if this is the direction from in which I am changing xk, so it's xk plus some other vector. And then I say, well, how far along pk should I be looking for my new iterate? So you can think of this like trying to find a new value of this argument that's going to make f smaller than it was before. Then if I take the original value xk and I add some step length times the direction, that this will tell me how far in the direction pk to go in order to get f to be as small as I can make it in that direction. So then I could try that new point and say, okay, let me try this new point xk plus alpha pk, for example. And if I try that one out, then that if I see like, okay, how long should alpha be? And I try different values of alpha, and then I see f of xk plus alpha pk is the smallest for one of the values of alpha that I try, then I can say, okay, let's try the new iterate, for example, is xk plus that alpha pk, where alpha is the one that I tried that made this as small as possible. Something like that you could think of as an idea for getting the different iterates. And so the trust region is about that you use an approximation of f. So this would be a case where you make an approximation of f, maybe related to like a Taylor series up to perhaps second order. And so let's say that we were to get some type of approximation of f, let's call it mk. And so at xk plus p, this is going to equal fk plus p transpose del fk plus 1/2 p transpose bk p. Maybe you would use some function of this type to estimate what the what this model function that you're going to use is. So this M is for a model function. And it could be here related to your function f. And then this would be like a Taylor series approximation of the function f, essentially up to second order, if this is sort of potentially related to the second derivative. And so you could think of maybe doing something along these lines, so reminiscent of Taylor series approximations of f, and looking at what it would be at xk plus p. And so given values at xk. So then what you want to do in this case is you want to find the direction and step. So you want to find the p that satisfies, find the p that minimizes your approximation of f at xk plus p. So the idea is that this is an approximation of your function f at xk plus p. It's reminiscent of a Taylor series approximation taken around xk. And then what you get here is then you say, okay, so I'm going to try to find the p that makes this approximation of f as small as I can, but I'm not going to look at just any p. I'm going to require that xk plus p is in the trust region. And the idea with this is that since this is an approximation of the value of the objective function, I don't really want to just try, I don't want to assume that it's valid everywhere. It's probably potentially only valid in some region around xk. And so then I'm only going to look at when xk plus p is in that region that I essentially trust to have this model function that is an approximation of f be approximately correct. And so then that if I do find this point or this p that makes the value of mk at xk plus p as small as it can be, then in the trust region, then that means that I have found a new iterate, this xk plus p, that makes my objective function smaller. That's the idea of this. And so now that we have a conceptual picture of it, we can talk a little bit more about the line search. So let's talk about the line search search direction. So search direction for line search. So the requirement here for this line search is that we need to get a PK where you can decrease f in the direction of PK. And so that might be something that was in the back of your mind as I was saying that we need to do this alpha times PK, and how big do we make alpha after you've already chosen this PK? You might have been wondering, well, how would we like guess a PK? Well, the answer is it's not quite so. That is just a guess. So what you want to do is you want to ensure that the PK allows f to be decreasing along PK. And so one idea is the steepest descent direction. Which is negative del fk. And so this is the direction along which f decreases the most rapidly. And that may be a bit surprising You may say, really? How do you know that? Well, here's how we can get the idea. So from Taylor's theorem, there is a part in Taylor's theorem that involves second derivatives. And so if you look back at your notes, you'll see that it says that, or that you can derive the following from that. Xk plus alpha p, or f of xk plus alpha p is equal to f of xk plus alpha p transpose del fk plus 1/2 alpha squared p transpose del squared f of xk plus tp p for some t in 0 to alpha. And if you go back and double check that you agree with that to make sure that you can see how this is derived. So we can see here that the rate of change in f along the direction p at xk is the coefficient of alpha, which, is p transpose del fk. So that's this part here. And so what we want to do then is we want to find what is the p that's going to minimize this. And let's say that we require it to be a unit vector. See if you can prove this to yourself, that this is true. So then, since P transpose del Fk is equal to, this is a dot product of P and del Fk, so we can write our normal dot product thing. Del Fk cosine theta is equal to, then since P, we already said that it has unit norm, where we said that is right here. This would then equal del Fk norm cos theta. And so theta is the angle between P and del Fk. And so then we can say, okay, so when is this as small as it could possibly be? So this is going to be as small as it can possibly be if cosine of theta is equal to -1. And so this would mean that P needs to be a unit vector. So hence the normalization here. So P needs to be like this. And so you can see that this is a unit vector that is in the direction that has this angle with del Fk. And so, meaning it's like 180 degrees different because cosine of theta is -1 at the 180 degree mark. So you can see that this is a case where it's like the opposite direction, but still a unit vector. So this is this leads us to the idea of the steepest descent method. Which is a line search using pk equals negative del fk at every one of the steps. And so it's taking the steepest descent direction. And so this has some benefits and some limitations. So that's going to be the theme of algorithm development for optimization, is that if you always choose your descent direction like this, then that's nice, and that you don't have to take second derivatives in any code that you would do to code out this line search algorithm using this type of step. But the problem is that this could be very slow on hard problems in practice. And so it can be demonstrated that any descent direction decreases f if the step length alpha is sufficiently small. And so what this means when we say it's a descent direction, this means that the angle is less than pi over 2 with negative del fk. And so to see that any descent direction will decrease f for a sufficiently small alpha, we can get some idea of this, again, going back to Taylor's theorem. And this time looking at, again, the second derivative part. But let's look at the case that we have f of xk plus epsilon pk equals f of xk plus epsilon pk transpose del fk. Plus, and then there's going to be some term over here that has an epsilon squared in it multiplied by some other stuff related to like second derivatives and things. So this means over here that it's order epsilon squared. So it means the epsilon squared multiplies in this term. So the if the pk is a descent direction, then the angle theta k between pk and del fk, we said that it would have cosine of theta k to be less than 0. So this would mean that pk transpose del fk is equal to pk del fk cosine of theta k. And so we can see that this will be negative if cosine of theta k is less than 0. So that's what we want here. And so as long as the angle right here is such that it will allow cosine of theta k to be negative, then this will be a direction where pk transpose del fk is negative. And so that's what we want. And so then what we can get is that f of, going back to this, we would get that f of xk plus epsilon pk would equal f of xk, and then there will be this like plus epsilon pk transpose del fk plus order epsilon squared. So this part here is going to be negative, and this part over here, if the epsilon is really small, this combo term here is going to still be negative, because even if this part was positive, if the epsilon is small enough, it's not going to outweigh the negativity of this part, because, for example, if you imagine epsilon is 0.01, for example, and this part's negative, then there will be some sufficiently, like if epsilon is 0.01 squared, it's much less than epsilon, which is just 0.01. And so there's some small range of epsilons where this part that's negative is still going to outweigh whatever's going on over here, and you're going to overall get that this part over here is negative. So this is going to be less than f of xk because it's xk minus something over here. And so this would be true that the f of xk plus epsilon pk is less than f of xk for all positive but sufficiently small values of epsilon. So this shows that I'm not limited to only choosing pk equals negative del fk. Like I could choose other directions as well and still get that I'm getting a decrease in f along that direction. And it might mean that I have to take epsilon sufficiently small to get that decrease over here, or that my step length, if this was alpha, would have to be sufficiently small for me to actually get a decrease in f. But you can see that then I would still be able to get it. So you can think of having other directions as well, instead of only the descent direction. You could have other directions as well. And so there's a lot of things about the numerics then of unconstrained optimization that will play into whether or not your algorithms are working well and how to do them. But this gives an idea of some of the main things that are involved in unconstrained optimization. So first, you have your theory of it, which tells you things like what has to be true at local minima or and vice versa. What things, if true, signify something as a local minimum. Those might be helpful in developing things like stopping conditions for algorithms, because what that means is like how long should you keep guessing, how long should you keep making new iterates? Well, if you meet certain conditions, maybe you can say based on these conditions, I can tell that I've reached a minimum. And so that's where some of the optimality conditions can be very useful. And then, so these algorithms are going to be iterative. So you're going to make an initial guess, and then you need an algorithm that develops a sequence of iterates that brings you toward the optimal value of the decision variables. What that means is that they have to be decreasing your objective function. And then we said, okay, well, how can I get iterates that decrease my objective function? We said, well, you could use line search or you can use a trust region. So in the trust region, which we spent less time on and we will spend less time on, the idea was to use some type of approximation of f, and then to find the vector p that causes this approximate function to be as small as possible. And so you can see then that the p here is not limited to like a step length times a pk. Instead, here you actually can be choosing the direction while you're doing this minimizing problem, versus over here, when you do the line search, you have to first choose a direction, and then you have to do this line search where you're searching for the alpha that makes this objective function smaller along when I'm changing the value of the decision variables along the direction pk. And so you can see over here that because this model function is only an approximation of our objective function, we only look at xk plus p in the trust region to see which values of xk plus p make this model function be small. And then over here, when we do our line search, what we do instead is that we try to minimize the function from xk plus alpha pk, and then we could say, okay, well, where am I going to get this pk? And we can say, okay, well, one thing you could choose is this negative del fk. And we said, well, how do I know that that's actually going to cause a decrease in the objective function? Then we went through and said, okay, well, Taylor's theorem is this. And so Taylor's theorem is going to tell me that the rate of change in f along the direction p at xk is the coefficient of alpha, which is p transpose del fk, which you're going to demonstrate it for yourself to make sure that you can see that. And then over here, we're going to find the p that is going to minimize this rate of change in F along a direction P, so that we can try to find the direction in which F is decreasing the largest. And we're going to require that it have a unit norm. And then we can demonstrate that if P is equal to negative del Fk over the norm of del Fk, that it's not only a unit vector, but also one which gives us the most the biggest rate of change in our objective function F along P, making it more and more negative. And then so that was important because when we went back to Taylor's theorem, we can see that though there are other directions that could also be chosen instead of just the negative del Fk type direction, and we could normalize this if we want to make sure Pk has a unit norm, that there are also other directions which could also decrease F as long as we are having our like alpha or epsilon over here be sufficiently small to ensure that regardless of what's going on in this third term, that the second term, if it is negative, which would happen if we have the right angle with negative del Fk, as we can see here, that then you would still be able to get your next iterate be less than your prior iterate F of xk. And so that's some ideas about the fundamentals then of unconstrained optimization. You can see how these could be used as the beginnings of the development of algorithms, and then those algorithms would have guesses and then would update the guesses according to things like line search and trust region. And then in the end, what you'd end up with is you would end up with stopping the algorithm when you meet certain criteria, which might be based on things about the optimality conditions. So that gives you some idea over here. And I'm going to go ahead and stop this recording.